Hello dear students, this is the lecture series on topology second MTH 802. In this lecture we are going to discuss normal space and regular spaces. So let's first define a normal space. Definition of normal space. A topological space X is said to be a normal space if it is first a T1 space. If it is a T1 space and any two disjoint closed sets and any two disjoint closed sets can be separated by disjoint open sets. That is if A and B are disjoint closed sets, then there exist disjoint open sets U and V such that a subset of U and B is subset of V. So a normal space is first a T1 space and any two disjoint open sets can be separated by disjoint any two disjoint closed sets can be separated by disjoint open sets. That is, if A and B are two disjoint closed sets, then there should exist two disjoint open sets U and V such that A is subset of U, B is subset of V. That is, if we have a topological space X, then we say this topological space X is a normal space if it is first a T1 space. So T1 space means that every singleton set is closed. If it's first a T1 space, second, if we have any two disjoint closed sets A and B, there should exist two disjoint open sets U and V, where U contains A and V contains B. This is U and this is V. That is the definition of a normal space. Next, we define a regular space. A topological space X is said to be a regular space. A topological space X is said to be a regular space. If each pair consisting of a point X and a closed set B and a closed set B with X not equal to B, such that X is not in B. So a topological space is said to be a regular space if given a pair consisting of a point X and a closed set B with X is not in B. This pair can be separated by disjoint open sets. That is, So in the previous case, both the sets are closed, but here B is a closed set, but X is not. X is just a point, which is not in B. So these X and B can be separated by disjoint open sets. So that is, there exist disjoint open sets U and V such that X belongs to U and B is subset of V, and B is subset of V. This is B here. B is subset of V. So a topological space is said to be a regular space if each pair consisting of a point X and a closed set B such that X is not in B can be separated by disjoint open sets. Separated by disjoint open sets means there exist disjoint open sets U and V such that X is in U and B is subset of V. So that's a definition of a regular space. So next we define a T3 space. So a T3 space is a regular space plus T1 space. So a topological space X is said to be a T3 space if it is first a T1 space, and second it should be a regular space. That's the definition of T3 space. T3 space. Definition of T3 space: a topological space X is said to be a T3 space. Is said to be a T3 space if it is T1 and regular space. If it's a T1 and if it's T1 and regular space and regular space. So a topological space X is said to be a T3 space if it's both T1 as well as a regular space. So now you can easily verify that every T4 space is T3 space. So that's an exercise for you. Every T4 space, every T4 space, can we say this, every T4 space is T3 space. Every T4 means I need to disjoint open sets. So every T4 space is T3 space. Every T4 space is T3 space. So let's suppose X is T4 space. So we need to show that X is T3 space. That means X is T1 space and regular space. Then X is T1 space, because by definition T4 space is first a T1 space. Then X is a T1 space. Now we show that it's a regular space. Now we show that it's a regular space. It's a regular space. So for this I choose a point and a closed set P such that X is not in B. So let X be in X and B is a closed set such that X is not in B. We show that X and B can be separated by disjoint open sets. Then this singleton X is a closed set. Because X is a T1 space, and in T1 space every singleton set is closed set. Then this is a closed set and it is disjoint from B, and these two sets, they are disjoint because X is not in B, as X is not in B. And the topological space is T4 space. By definition of T4 space, any two disjoint closed sets can be separated by disjoint open sets. So therefore, the singleton set X and B, they are both closed and they are also disjoint, therefore can be separated by disjoint open sets. Thus, the singleton set X and the set B can be separated by disjoint open sets. That is, there exist disjoint open sets U and V such that the closed set singleton X is subset of U and B is subset of V. So this implies X is in U, X in U, and B is subset of V. So thus the pair consisting of a point X and a closed set B such that X is not in B can be separated by disjoint open sets. So therefore X is a regular space. Therefore X is a regular space. It's also a T1 space and a T3 space. It's a T1 space and regular space. So hence X is a T3 space. Is a T3 space. So next we prove a theorem in which we show that every compact Hausdorff space is a normal space. It's every that's the theorem. Every compact Hausdorff space. Every compact Hausdorff space is a normal space. Every compact Hausdorff space is a normal space. Proof. So suppose X is a compact Hausdorff, sorry. It's a compact Hausdorff space. We show that X is a normal space. We show that X is a normal space. And by normal space we mean that any two disjoint closed sets can be separated by disjoint open sets. So let's take any two disjoint closed sets. Let A and B be two disjoint closed set. Let's take any two disjoint closed sets A and B. So we need to show that they can be separated by disjoint open sets. So in case if A is the empty set, then we choose open set. Then take U is equal to phi, or you can say G is equal to the empty set, and H is equal to whole space. Then take this and so now you can write here by taking G is equal to the empty set and H is equal to X. Then this G, then this A, it is subset of G, and that B, it is subset of X. So therefore in that case, sorry, subset of here H is equal to X. Therefore, in that case, A and B can be separated by disjoint open sets because G and H are disjoint open sets. G is equal to 5, H is equal to X, so their intersection is the empty set. So in that case, we are done. Similarly, if B is equal to 5, then we are again done. So thus, in this case, we are done. Thus in this case, we are done. Similarly, the case B is equal to the empty set is trivial. Is trivial. So now we assume that both A and B are non-empty. Assume that A is not equal to 5 and B is not equal to 5. B is not equal to 5. A and B are closed subsets of X. X is a compact space, and we know that a closed subset of a compact space, compact set is compact. Since A and B are closed subsets of a compact space X, so therefore they are compact. Therefore, A and B are compact. So because we know that every closed subset of a compact space is compact, so A and B are compact sets. They are closed subsets of compact set, therefore they are compact. Now let's choose a point. Let's choose a point X in A. Let X be in A, then X is not in B. So therefore B is a compact set and X is not in B, and for all X in A, this X is not in B. And we know that in Housdorff space, if we have a compact set B and a point X which is not in B, then these two, then this pair X and B can be separated by disjoint open sets in case of Housdorff space. Then X and B can be separated by disjoint open sets. Can be separated by disjoint open sets. Say Gx and Hx, because these open sets, they depend on X, because for each X in X, this X is not in B, and for this pair which depends on X, actually there exist two disjoint open sets. So let's denote those open sets by Gx and Hx. Now you can easily verify that this class, let's take this class cursive A, which is can be separated by disjoint open sets Gx and Hx. So let's write here such that this X is in Gx and B is subset of Hx. B and this point X, they can be separated by disjoint open sets. X is in Gx, B is in Hx. So now let's take this class Gx where X is in A. Then this Gx, because each such Gx, it contains X. So it means that the set A, then this A, it is subset of union of Gx, X is in A. So therefore, fancy A is an open cover, is an open cover of A, and hence can be reduced to a finite subcore. Hence can be reduced to a finite subcover.